I'm Vivek, and welcome back to this mini series on PIN for wearables. Last time we spoke about all the basic commands and ways of thinking in JAX and Python, which we'll be requiring for the other videos and tutorials in this series. So today we'll be talking about data pre-processing. So in any data science or machine learning pipeline, you typically do have this stage of data pre-processing, and after that, after you do that stage, you get some sense of what your data set looks like, what it feels like, what its contents are, and then you might realize that, oh, I need to focus on one specific segment of that data set. So after pre-processing, you typically follow up with segmentation and you extract the specific parts of the data that you want to focus on or you need to build your mathematical models on top of. And then you'll build those mathematical models and deliver metrics and complete that pipeline. So our mathematical model is the PIN, or the physics informed neural network. And the videos I have been putting out have been focused on coding up pins specifically in JAX. So that being said, last time we spoke about all the Python requirements, and today we'll be diving into this short video on data pre-processing. So I'll just briefly tell you about the problem at hand. So this is part of a project I did for a technical interview for a research engineer position at a top level consumer tech company in the Netherlands. And the problem at hand is that you have something known as an IMU sensor, which is available in your phones. It's there in aircrafts, it's there in robots and self-driving cars. And this sensor is used to figure out how your object is oriented and positioned with respect to the environment. So if you think of an aircraft, it tells you what the aircraft angles are, or you can think of an example in sports where, let's say, you have a cricket bat with a sensor on top and you're swinging it. It'll tell you how the cricket bat is oriented in space and the various angles the cricket bat makes with the planes. So this is possible if you place this IMU sensor on the cricket bat. So this is a very well-known problem in this field of navigation, robotics, biomechanics, and control, is the one of estimating orientation from noisy IMU sensor data. So that is the problem at hand. And I was provided with a experimental data set where the data set just contains a lot of information collected from experiments with these IMU sensors placed on an object, and they also provide you with reference data to see if your answer is correct or wrong. And the goal is to figure out what the orientation of this object is at a given time as it is moving and rotating through space. So the very first step we need to do once we are comfortable with Python and JAX is to actually just get a feel for this data set and understand what portions of the data can we work with and what data is redundant or useless, so we can throw it away and focus our attention on parts of the data set which we'll actually need or which actually contains the information you require to build your pipeline, right? So it's just removing redundancy and getting a feel for the data set. So that introduction being said, let's actually get to opening the notebook. So I have opened the notebook here, and just a quick note about installations and Jupyter notebook. So as I mentioned in the last lecture, I will not be guiding you through installations of Anaconda, Jupyter Notebook packages, and navigating through Jupyter Notebooks. This is very common knowledge. You can easily get help from ChatGPT or just find short YouTube videos about how you can go about doing this if you don't know how to, or if you don't have these things installed. Um, and as I've mentioned, our goal is to keep every lecture self-contained, as self-contained as possible. Because this is a mini series, we will be referring to past video lectures, at least the foundational one, but we'll still try to keep everything as self-contained as possible, which is why I'm mentioning this point about installations. I already did mention that in the last video, but since this is a very small point, it can be mentioned again for the sake of keeping things self-contained. So just bear that in mind that we won't be walking through installations. Please use ChatGPT or YouTube and Google, or take help from your friends if you don't know how to set these things up. So now that we have discussed like installation briefly and sort of set the stage for what we're going to do today, let's dive right into it now that we have the Jupyter notebook open. So, as I said, the goal for today is we just want to get a feel for this data set, sort of pre-process it, actually focus our attention on the information which is useful and get rid of information which is redundant, and get a sense of how the data is laid out. So that is the goal. Okay. So the first step is always importing libraries, right? So here we go. I'm just going to run this cell. We are importing pandas and numpy. So panda is a standard Python library for data wrangling, and it's designed to mimic Excel spreadsheet functionality. So it's meant to read in the data like it were an Excel spreadsheet and have it in that format. That is sort of what pandas is about. And numpy is just a numerical processing standard numerical processing library in Python, which we'll actually need to do some small, like, back of the envelope calculations or computations to figure out what portions of the data are redundant. Okay, so now that we have imported the libraries, the next thing to do is to actually load our file. So our file is this log file, and the code is very self-explanatory. So you just require the file path, that is where the file lives, and we need to open that with this command with open, and R just means read mode. So you're going to open this, and then you're going to just read the lines in this file and then assign that to data. That's very self-explanatory. It's just standard procedure while reading in a file. The R just means read mode, and with opens means just open the file at this path. This is where it lives. Read it, read all the lines, store it in this variable called data. So let's just go ahead and run this cell with shift enter. There we go. The data is loaded. So the first thing we would want to ask is, what does the data look like? So I'm a very visual person, so I usually just like to double click on the file and sort of look at it and get a sense of what it's visually like, because then I can write my code accordingly to pre-process the data. So now if you actually look at it, you will see these a bunch of double slashes initially and some information that's like the high level of the metadata, and then you can actually see various columns with the column headers and the actual data starts. So pandas is very nice. It's designed to read in data which sort of mimics Excel spreadsheets. So there's a command which is like, I think, pd.read_csv, where you can read these files in using pandas, but you do have to tell it where the actual data starts and the metadata ends. That is why we had to open up this file and sort of look at it, because now we know the actual data starts after these backslashes are over. So now the next thing to do is to locate where the actual data starts. So let's go ahead and figure out how to do that. So recall, last lecture we spoke about the enumerate operation, and we will actually need it here. Why is that? So we have data, and that data is stored as a bunch of lines. So, and you can iterate through this data, so you're iterating through these lines, and you want to find that line, the last line after which there's like that double backslash stops. So you want to actually find the index of that line. And once you find that, you want to sort of quit the loop or the iterator, right? And you want to store that index, which is why we'll need enumerate, because we want to loop through the lines in the data, but at the same time, we need access to the index. So what we need to do is we need a variable to store where the data starts. So we'll call that data start index. We'll assign none to it because we want to initialize it, and we don't have any information about what it is before we do the pre-processing. Then we are going to use enumerate through loop through the lines in this data along with the index. And then what we do is we want to see if the line starts with the double backslash, right? And then what you want to do is you want to see if the line does not start with a double backslash. The first line where things it does not start with it, that is where you know that metadata is over. So what you say is line dot starts with and the double backslash not means you're negating that, and if. So if this condition is not met, meaning if the line does not start with this double backslash, that's where at that index, that's where your actual data is starting. So then you say data start index is equal to index, and then you just quit the loop. So then you basically iterate through this. You have this if condition, you assign the index at which this condition is met, and then you quit the iterator by a break. So let's just do shift enter to like run this cell. Now that we have run this well, we have figured out the index. The next thing we need to do is actually now read the data in using pandas the pd.read underscore csv command, and we'll have to supply this start index to it. So again, the code is very straightforward. It's very readable. So you just say pd.read underscore csv, the file path, that's where the file lives. And you say skip rows is equal to data start index, which means that just skip all the rows until that line, right? And then it's going to read it and it's going to assign all that to something called a data frame. A data frame is like this data structure which is very, very similar and has the format of an Excel spreadsheet. That's all we need to know. So we'll just go ahead and run this line using shift enter. Great, that's done. So now that's done, let's actually start looking at some of this data, just investigating like the very basics. So like if we sort of scroll up and look at all this, you'll see the sample time fine, and that sort of just refers to the timestamp. So you have an object which is rotating and moving in space, and you have a sensor placed on it, and as time goes along, you're collecting data, right? So the sample time fine, that column in your data frame, just refers to all the timestamps. And it was mentioned in the problem statement that the timestamps was in the units of 10 to the minus 4 seconds. So if you want it in the standard seconds format, we'll have to multiply it by 10 to the minus 4, something to keep in mind. So now what are like some very basic things we can check with this timestamps column? So the first thing we would want to do is actually look at the difference between successive timestamps, and we can just use the diff command to do that. So, and because if we look at the successive differences, and if we find that all of them are positive, that means that the timestamps are increasing, or that just means that there's nothing weird about your clock. It means that you're actually collecting data and those data packets are coming in as the data is being collected. It doesn't mean that the packet at 5 seconds comes in before the packet at 1 second. It just means that your data is not scrambled up randomly. It means that the order in which the data was sensed and collected, your data is being received in the same order. So that is the first check we want to do, right? So the first thing we do is we have a pandas data frame, and that's like a Excel spreadsheet column. So we are interested in the values in this sample time fine. So you just say df square brackets name of the column, which is sample time fine, dot values. This will give you all the values, and we want to explicitly store it in data containers having specific types. So we want to keep things in a numpy array because later on we'll be doing some mathematical computations with it. So we do df square brackets sample time find dot values to extract the values corresponding to the timestamps from that column, and then we want to convert that to a numpy array. So you say np dot array and just pass this to that and assign that to t underscore array variable. Then we are going to take the diff using numpy dot diff, and as I said, like, we want everything in second, just a standard unit. And the problem statement, it was mentioned that the unit was 10 to the minus 4 seconds. So we multiply by 10 to the minus 4 and we get this difference or dt array. Then this code is very self-explanatory. We just say dt array greater than 0 is like a boolean. It just figures out how many of these elements are positive. All of dt array greater than 0 means are all of them positive or not. It's a boolean, true or false. If that means if all of these differences are positive, then you just print out the timestamps are in the correct order. There's no scrambling. Okay, so that's like the first thing we need to do. The second thing that we actually care about is the data being sampled uniformly, meaning that you're not, when you collect data, your time, even though in an abstract mathematical sense is continuous, you don't collect continuously. You collect at discrete time points which are spaced out, like maybe 0 seconds, 0 0.1, 0 0.2. So you want to know if the order is something like 0, 0 0.1, 0 0.2, 0 0.3, and not something like 0, 0 0.1, 0 0.2, 0 0.5, 0 0.6. So you're looking at maybe the differences being the same, being constant, meaning like the sampling time is uniform and there's nothing strange about the sampling rate. So what that means is you actually want to figure out if this dt array has just, like, you want to look at the unique values in this dt array and figure out if there's only one unique value. Okay, so then you just use the command np.unique of dt array, and that gives you like all the unique values. So you just say dt underscore unique underscore array is equal to that np.unique of dt array, and then we look at the length using the len command. And now if this length is 1, that means there's only one unique element and the sampling rate is fixed. And then we can retrieve that using the dot item command. So then we say dt is dt underscore unique underscore array dot item, and then we can print it out. And while printing it out, we are using f strings, which means you say f and then you have the double inverted commas. You have a string, and then wherever you want to print something numeric, you put these curly brackets and put the quantity you want, it's dt, and then we want to print out till the first decimal place, so you put a dot 1e. So let's just run and see what we get. So great, our timestamps are in the correct order, the sampling rate is fixed, and the sampling interval is 2.5 10 to the minus 3 seconds, which means it's 2.5 milliseconds. So that's very great. We have really nice data to work with. So now let's move on to the next item. So it's really great that our data has been read in, our timestamps are not scrambled, all the data is being like received in a nice order and it's received uniformly, so it looks like our data is really good. The next thing we want to do is see if some columns are useless or redundant. Now this is like a physics data set, right? And let's actually just go back and look at the names of the columns, so we'll get some sense of how this redundancy might actually be coming into play. So if you look at this packet counter, is just maybe a reference tag to these packets coming in. Sample time find is the timestamps. And this ACC underscore XYZ, these refer to, like we said, we have an IMU sensor. An IMU sensor has another small sensor called an accelerometer, which measures accelerations inside the sensor frame. So these ACC just refer to accelerometer readings, which are some measures of accelerations, local accelerations, and the x, y, z are just the three components, right? And the same way you also measure angular velocity in this local frame using a gyroscope, and the g, y, r refer to that. So these clearly, like the first columns are just the times and accelerations, angular velocities like locally. And then you see there's vel inc x, vel inc y, vel inc z or z. This you can clearly tell are like the velocity increments, how much the velocity is incremented. And then here you have Ori Inc. Q0, Ori Inc. Q1, Q2, Q3. So these are like the orientation or inclination, um, orientation like increments or changes. So it's clear that what we basically are dealing with is that we have our timestamps, we have the packets, and we have local acceleration readings, the three vector components, local angular velocity reading, three components, and increments in the velocity, increments in like the orientation. So like our intuition clearly dictates, like this is like known from basic physics, that your velocity increments are just going to come from a rate of change of velocity with respect to time multiplied by the small time intervals. That's just acceleration into dt's, right? And your orientation changes are going to come by from like the orientation change per unit time into dt, which is like the angular velocity into dt, something of that sort. So the orientation part is slightly tricky, but first let's just actually go through like the velocity increment part. So it's very clear, like the x acceleration into dt and the velocity increment x, they should be related in some way. So now like they might not be exactly same, because numerically things are always like they're not exact. It's not pen and paper calculation, there are numerical errors. So what we can do is we can first just get um like the column corresponding to like acceleration x, so that's df accx, right? Multiply that by dt, then you'll have the velocity increment x. We can just take the difference, and once you take that difference, you can convert that to a numpy array, right? This you now you're going to get an array of these differences. They shouldn't be exactly zero. Some will be positive, some will be negative. They should be close to zero, maybe, maybe not. We can take the absolute value to just get a sense of like how large they are. And that's an array, right? And now we can just do basic statistics on this array. We can extract the maximum value, the mean, and the minimum. And if these numbers are small, that just tells us that, oh, like this, both these columns are not required, we can throw away one column. And typically with IMU sensor data, it's very standard practice to get the acceleration reading, that is the actual experimental data. It's very rare to see velocity increment data being provided. So I would be personally skeptical about where this velocity increment data is actually coming from. Have they actually done some pre-processing and provided this to us? So in case I have to make a choice and it turns out that there is redundancy, like these both these columns have almost identical data, I would throw away the velocity increments and stick to the accelerometer data, as that is very standard practice. So let's just go ahead and run this cell. So as you see, like the max is of the order of 10 to the minus 4 for x, y, z components. The mean is of the order of 10 to the minus 6, and the mean just says 0. So it's clear like both the columns have the same data, and that means the velocity increment data can be thought of as redundant. We want to throw it away. As we said, it's more typical to stick to like the actual experimental accelerometer readings. That's very common. I really don't know where velocity increment data comes from. So we'll just say it's redundant and throw that away. And now the last check we need to do is for like the orientation increments. Now here is where the tricky part comes. The tricky thing is that to actually know how the orientation increments are related to the angular velocities, you actually need to understand the governing equation, which uses mathematical entities called quaternions. And since we want to keep this video self-contained and learn to think in context, you might or might not know about quaternions, or you might have heard about it and forgotten about it, and you might be given this assignment or this problem to solve. So in that case, you might have to quickly look up the relation between quaternions and angular velocity. And since I'm not telling that to you over here, I'm going to tell you how you would actually approach this from first principles if you didn't know anything about this. So let's just think from common sense. You know, the gyroscope is like an angular velocity, right? So it is a rate of change of some kind of angle. So if you multiply that by dt, you're going to get some measure of an angular, like change in angle in a small time, right? And you have been given like four columns. So you have ori inc underscore q0, q1, q2, q3. So you know that one of these four columns, if there is redundancy, should in some way relate to how the angle is changing in that small instant dt. Okay. Now, the thing is, the simplest thing is it is just the rate of change into dt. But if you abstract that one step further, like if you think about it mathematically, when you say that you have a rate of change with respect to time, like some measure of that, you multiply that by dt and that equals another column. Mathematically, you're just saying that they are linearly independent and the linear dependency factor is dt. But it doesn't have to be dt, right? If you like generalize this idea further, you are just saying that I have two columns and they're like, if you go away from the physics and think about the mathematics, so we say that by common sense, maybe these two columns are related and they might be a factor. From physics, you might expect that factor naively to be dt. If you know the equation, you might realize that there is some change to dt or it is just dt. But mathematically, you can say based on common sense and some knowledge of physics, these two columns might be related and there might be some factor like dt, but you don't know what it is. Now, if you don't know what it is, you can just say maybe they're linearly dependent. And also, you don't know like the gyroscope X, right? You might not know which of the Ori columns it corresponds to, whether it's Q0, Q1, Q2, Q3. So if you didn't know anything, what you could, like the very, very crude way of actually looking at this is you could have actually looped through those four columns, right? And for every column, you could have just taken gyroscope X and you could have just said like this is X. This is like you could have thought of your gyroscope X as as a like a column vector A. You could have thought of the df orientation as a b, and you could have said, is there some alpha or x which solves this equation ax is equal to b, right? And you could have actually done that very crudely, running through various values, and you know that it's some factor of dt. So it could be maybe something ranging from 0 to 2 times dt or 10 times dt. So you could have set up a while loop going from 0 to some 10 times dt and done it very crudely, or just used linear algebra solvers to figure out if it solves the equation ax is equal to b. So there are ways to go about this using common sense, even if you don't know the quaternion equation. So here the factor is dt by 2, and I know this because of the quaternion equation, which I sort of looked up. I had forgotten about it, but I know what quaternions are, so I could quickly look it up and figure out, do some math and figure it out. But the point is, even if you don't know this about this factor dt by 2, by physics, you should know that a rate of change, right, should be related to an increment and they should be some factor like dt. But it might not be dt, but it might be related to dt. Then you can think mathematically and realize that, oh, this is, we are just talking about a linear dependence between the gyroscope x, which is the rate of change, and one of the columns. And we don't know what the factor is. And just based on that, you could have actually written some lengthy code and non-optimized code to actually figure out which column gyroscope x is linearly dependent to and with what factor. And then you could have said that since all directions are maybe symmetric, that factor is constant across all. You could have made that assumption and then check for the other columns like the y and z components. So that's how you could have actually approached this from first principles, just by a basic knowledge of physics, math, linear algebra, and common sense, right? And in data science, I guess it's, if you don't know much about the data set, you can always look at columns being linearly related. So that's how actually you would go about this if you did not know about this factor dt by 2, which you don't, so I'm telling you how to. But anyways, I've told you the whole process of how you would approach this if you didn't know it. But for now that I've told you about this process, we'll just stick with this factor dt by 2, which comes from the quaternion differential equations for angular movement. And we'll go through the same process, right? So we'll say df of like gyroscope underscore x into dt by 2. We'll take that. We'll take df o-ring q1, subtract that, convert it to a numpy array, take the numpy.apps to get like a magnitude, like a distribution of magnitudes, and then we'll do basic statistics, look at the mean, max and min, and if they're really small, it means that one of these two columns can be thrown away. But since it's standard practice to give experimental data for local measurements of angular velocities via a gyroscope, it is better to stick to that and be on the safe side and throw away the increments and say that they're redundant if these statistical numbers turn out to be small. So let's go ahead and run this code. So this runs, and as you can see, again, the max values are of the order of 10 to the minus 7, the mean is 10 to the minus 7, minimum is 0. So again, the orientation increment data is redundant. So okay, closing remarks. So we've sort of gone through this standard data pre-processing exercise, which is just going through the motions when you're working through a data science or an ML pipeline. But we're obviously solving like a physics problem in the domain of motion tracking, very relevant to applications like sports, biomechanics, robotics, navigation, and self-driving cars. And this is a well-known famous problem of orientation estimation from noisy IMU sensor data, which consists of accelerometer and gyroscope readings in a local body fixed frame. So we have sort of been given this industry grade sensor data and in this log file, and we have like read in the log file, used pandas to sort of um, read it in like an Excel spreadsheet, and we had to sort of look at the data, throw away the metadata. We used enumerate, and then we just investigated like the timestamps just to see that the data is coming in cleanly, it's uniformly sampled, and then we looked at redundancy and used very basic knowledge of like physics, common sense, and linear algebra, and some statistics to throw away columns. And that's it. That's the data pre-processing pipeline. And I hope you enjoyed this video. I hope it was self-contained. Like the idea was to, like, at least with this quaternion orientation increment part, like one of the goals here was to explain this to you with the mindset that you don't know anything about this and how you might have approached this had you not known things about this. But if you do know a little bit about quaternions, and if you were given an assignment like this, you can always Google some important papers, look at YouTube videos, ask ChatGPT to quickly figure out this equation and sort of go from there. So yeah, I hope you have enjoyed this video. This is a slightly different data pre-processing video than ones you might have seen, simply because it pertains to a physics problem and I am a physicist, so that's what I do. So hope that you have enjoyed this video. Now that we have pre-processed the data, the next video is actually going to be about segmenting the data, meaning that we have figured out what this data looks like, what columns are useless, what columns we care about. But in the columns we care about, there's actual data, and that data has structure. So in that structure, like what does that structure mean, right? If we actually look at the accelerometer readings, what does it tell us? And do we really need fancy PINN-like algorithms to crunch the data and get insight? Or can something very crude be used? And can you actually segment it to say, oh, this portion is really simple. I know the answer by looking at it and doing some basic back of the envelope calculations. This portion is hard, PINN can be used, but it's too challenging to use a basic PINN. This is where PINN can be used to show proof of concept. So it's about getting a more in-depth sense of what the useful information in the data actually means. And to do that, you actually have to dive deep and segment it up, cut it up before we go to the pins. So that's what will happen next time. We'll actually talk about data segmentation. See you in the next video lecture. Peace.